Hi guys, welcome to a lesson of ordinary differential equations. So in the previous class, we discussed about the first order linear differential equation of the form y prime plus p of x times y equals q of x, right? So an equation of the kind is called the first order linear differential equation, right? So today we are going to talk about nonlinear first order differential equations. And more specifically, we'll talk about Bernoulli's equation. And then in the next class, we'll talk about Ricciardi's equation as well. So let's start with a form that f prime of y dy by dx and then plus p times f of y equals q, right? So this is a kind of nonlinear differential equation where we have a function of y here and a derivative of the function. So if we have an equation of this kind where we have a function of y here with p is just a function of x or a constant. It may be a constant, right? Constant, and same to the q. It may be function of x or a constant. And then we have this f of y, so a function of y, and this f prime of y just represents that this is the derivative of that function that is here, f of y, right? So we'll take some examples and we will solve them to see that how to proceed for these types of problems, right? So let's take a problem here, and question is given that dy by dx plus x sine 2y equals x cubed cosine squared y, right? So now we have function of y here. This is function of y, this is also function of y, and to make it into the standard form, because we only need a function of x here, that is q of x, to make it compatible with the standard equation, we will divide whole equation by cosine squared y. So it will be 1 over cosine square y, and we will write y prime instead of dy by dx plus x times, and for sine 2y we can write 2 sine y cosine y, that is the angle identity, divided by cosine squared y equals to x cubed. And then we have this sec squared y times y prime plus x times this cosine y will cancel with this, and sine over cosine will have 2 times tangent y equals x cubed, and some further simplification will lead us to this form. And that is what actually we need. And this is the standard form. And we can see here that this tangent y here and sec squared y, so f of y in this case is tangent y, where f prime of y is simply sec squared y. So the derivative of tangent y is sec squared y, and so now we can proceed for the solution of the problem. For that, we can just consider let u equals tangent y. So we will get du over dx equals sec squared y times dy by dx. So we can replace this function here. So we can write du by dx for that. Simply it's du by dx plus 2x, and for tangent y we can write u equals x cubed. So now it's a linear first order differential equation. So we can find the integrating factor. It will be exponential to the power 2x dx. So we'll have e to the power x squared. Now we can just multiply this e to the power x squared, or just we can write in the standard solution form. So u will be equals to 1 over e to the power x squared times the integral of x cubed times e to the power x squared dx plus c. So this is our u, right? And now to solve the integral, we can use by part rule here. So, or we can just write in this form, e to the power x squared integral x times, sorry, x squared times x times e to the power x squared dx plus c. And then we can see here, or we can also use a substitution. Let's assume that t equals x squared, which implies that dt equals to x dx. So we can replace here, just taking this integral, we can write 1 over 2 times x squared, oh sorry, not x squared. In terms of t, we should write here. So x squared is equals to t. And for x dx, we can write dt over 2. This implies that x dx equals to dt over 2. So this 1 over 2, we move it outside, and t to the power t dt. So simplifying the integral, we will get this solution. So we will plug back. This implies for t, we have x squared e to the power x squared minus e to the power x squared. So plug here, we will get u equals 1 over e to the power x squared times 1 over half x squared e to the power x squared minus half e to the power x squared plus c. So this is not the final form because we initially assumed a solution. So now we have u equals 1 over 2x squared minus half plus c e to the power negative x squared. And for u, we have tangent y. So it will be half x squared minus half plus c e to the power negative x squared. So we can just leave the solution here, and this is the solution, or we can write y equals tan inverse times the function of x here, right? So this is simply the solution for this differential equation. All right, so let us consider one more equation, one more example. So let's say this is dz over dx plus z over x ln z equals z over x squared ln z squared. Now again, this is not in the standard form, so To make it into the standard form, we have to divide the whole equation by this function, this z times ln z squared. So we can do here z times ln z squared plus this will be ln z z ln z over x times z ln z squared equals 1 over x squared. And then we have some cancellation here like this, and I forgot to write z prime here for dz over dx. So z prime equals dz over dx. Now we have z prime over z ln z squared plus this cancels with this one, this z cancels with this. So we have 1 over x ln z equals 1 over x squared. Now we can see that this is 1 over ln z. So the function of z is simply 1 over ln z. And we can see that f prime of z will be equals to ln z times 0 minus 1 times 1 over z over ln z squared. So this will be so f prime of z equals negative 1 over z times ln z squared, right? So the derivative is present here, but negative sign is absent, but it doesn't matter. We can just assume that u equals 1 over ln z. And then we have to find du over dx. That will be equals to negative 1 over z ln z whole squared dz over dx, because we already computed the derivative here, this one, right? So now for this, I can replace 1 over z ln z squared z prime equals negative du over dx. Therefore, we will have negative du over dx here and plus. Then for 1 over ln z, we can replace u. That is here in the equation for 1 over ln z, we can replace u. So it will be u over x. And then equals to 1 over x cubed. So we can just do some more simplification to make it in the standard linear form. Now it's a linear first order differential equation and easily solvable. Okay, there's one mistake here. Sorry, it's x squared, not x cubed. So it's x squared. And we can check here also. So it's x squared, right? Now the integrating factor will be e to the power negative 1 over x dx, which means we have 1 over x as the integrating factor. And the solution will be, so it's mu of x, right? So the solution will be 1 over x integral 1 over x times negative 1 over x squared dx plus c. And then we can just simplify this integral. So u equals x times integral of negative 1 over x cubed will be negative positive 1 over 2x squared plus c. So u equals 1 over 2x plus cx. Okay, so now u equals ln z, sorry, 1 over ln z. So we can replace here 1 over ln z equals 1 over 2x plus cx. And here is the answer. So in this way, we can solve the problems on first order nonlinear differential equations. And for the Bernoulli's equation, in the next class, we will discuss about the Bernoulli's equation. So that's all for the time being. Thanks for watching the video.